Section: Introduction. In this section, we discuss the rapid rise of large language models, LLMs, like GPT-4 and others, which have become essential in natural language processing and AI due to their extensive pre-training and transformer designs. This pre-training gives these models impressive abilities in various areas, including math and coding, without needing specific training for each task. However, real-world applications often require models to be tailored to specific tasks, using particular terminology or response styles. To meet this need, we focus on parameter-efficient fine-tuning, PEFT, which introduces a small set of adjustable weights, particularly through low-rank adapters like LoRa. While LoRa helps keep the number of adjustable parameters low, the time and resources needed for adaptation remain significant. For instance, adapting a smaller model like Qwen 2.5 with LoRa can still require substantial computational power. Additionally, each user or dataset necessitates its own optimization, which can become a major hurdle when scaling PEFT. We recognize that a LoRa adapter essentially functions based on its training data, where gradient descent adjusts the base weights toward a specific task. If we could learn the mapping from prompts to weights directly, we could eliminate the need for gradient descent. Previous research has shown that hyper-networks can quickly generate large numbers of weights, but they often overlook task-specific details or rely on simplistic embeddings. Recent advancements have made it possible to condition these generators on task information effectively. Our approach, drag-and-drop LLMs, DND, is a prompt-conditioned hypergenerator that transforms a few unlabeled task prompts into complete LoRa adapters in seconds, removing the need for task-specific optimization. DND uses a lightweight text encoder to create conditional embeddings from prompts, which a hyperconvolutional decoder then expands into LoRa updates for each transformer layer. In tests involving reasoning, math, coding, and multimodal tasks, DND significantly reduces adaptation time while improving performance on new datasets and smoothly transitioning between different model sizes. By streamlining the traditional process of generating weights, we challenge the idea that gradient descent is essential for model specialization, suggesting a new approach where weights can be generated based on concise task descriptions. Our main contributions include a new paradigm for LLM adaptation, a practical architecture that minimizes adaptation time, and comprehensive evaluations demonstrating DN's efficiency and versatility. Before we delve deeper, we identify key challenges we face. First, we need to ensure our parameter generator can effectively adapt LLMs to specific tasks. Second, we aim to achieve this adaptation without requiring task-specific training. Lastly, we want to make the drag-and-drop functionality user-friendly and accessible for broader use. Section Summary. In this section, we introduce drag-and-drop LLMs, DND, a novel approach that generates task-specific LoRa adapters directly from unlabeled prompts, significantly reducing adaptation overhead and eliminating the need for per-task optimization. Our method leverages a lightweight text encoder and a hyperconvolutional decoder, achieving up to 30% performance gains on unseen datasets while maintaining efficiency across various model sizes. Section: Overview of DND. In this section, we present an overview of DND, as shown in the accompanying figure. To tackle the challenges we've identified, we first train and save LoRa adapters on different datasets. Our goal is to create a drag-and-drop capability, which requires us to understand how parameters relate to datasets. Therefore, we randomly pair checkpoints with prompt batches from their training data. We then use a pre-trained text encoder to extract embeddings from these prompts, which we input into our parameter generator. This generator has a straightforward design consisting of stacked convolutional decoder blocks, as detailed in the following sections and appendix. We optimize the generator by minimizing the difference between the generated and original model weights using mean-squared error. During inference, we test our method in both in-domain and cross-domain situations by simply inputting prompts from new datasets that were not part of the training process. This allows us to obtain customized model parameters in a single forward pass. Next, we address how to effectively use these elements to give D&D its drag-and-drop training ability. For a given dataset, we split it into distinct prompt batches. We denote the trained LLM checkpoints for this dataset and randomly select a prompt batch along with a corresponding checkpoint. This pairing serves as the basis for training our parameter generator, where the prompt acts as input and the checkpoint provides supervision. For each prompt batch, we utilize an open-source text encoder to extract embeddings that will be fed into the parameter generator. This extraction process is defined by a function that produces embeddings corresponding to each prompt. We typically use an encoder-based language model for this purpose, but we also explore other embedding methods, such as Word2Vec, encoder-decoder architectures, and decoder-only models in our experiments. In terms of inference, we aim for the parameter generator to effectively handle new datasets or tasks that it hasn't seen before. Our evaluation focuses on performance with these novel datasets, following a four-step process: sampling prompts, extracting embeddings, inputting these embeddings into the parameter generator, and assessing the generated parameters on the new datasets. We evaluate our method's drag-and-drop capability in both in-domain and cross-domain scenarios. For implementation, we select the Qwen 2.5 series as our foundation model and conduct experiments across various tasks, including common sense reasoning, coding, math, and multimodal tasks. We provide details on model sizes and datasets in the accompanying table. We use SentenceBERT as our default text encoder, with specific prompt batch sizes for each task. To further investigate DN's zero-shot capabilities, we tested not only on in-domain datasets but also on cross-domain tasks. We use checkpoints trained on common sense reasoning and evaluate them with prompts from different domains, comparing the results with those from training LLMs on science datasets. Our findings indicate that D&D outperforms the average accuracy of its training LLMs, demonstrating its ability to adapt to cross-domain tasks. We also apply D&D to coding, math, and multimodal tasks to validate its effectiveness in more complex scenarios. The results confirm our method's success in text modalities, and we further explore its potential in other modalities. We fine-tune the Qwen 2.5-VL3B model on a multimodal dataset and evaluate its performance, showing that D&D can be effectively adapted beyond text. In summary, D&D proves to be a robust zero-shot learner with broad applicability, as evidenced by significant improvements over training data and promising results across various scenarios. We look forward to exploring more intriguing features of our proposed approach. Section Summary. In this section, we introduce D&D, a method designed to enhance model adaptability through a drag-and-drop capability by training a parameter generator on various datasets using prompt checkpoint pairs. Our approach demonstrates strong performance in both in-domain and cross-domain tasks, showcasing its effectiveness across multiple modalities, including coding, math, and multimodal applications. Section: Ablation Studies. In this section, we explore several interesting features of our approach. We provide additional details about various experimental settings in the appendix for completeness. Unless stated otherwise, we use ArcC as our test set and other common sense reasoning datasets for training. We compare the performance of our D&D method with that of foundational large language models, LLMs. We recognize that while LLMs benefit from extensive pre-training, fine-tuning them on a small dataset can hurt their performance on new test sets. To address this, we evaluate the performance of D&D generated weights against foundational LLMs across all tasks in our experiment. Specifically, we use Qwen 2.5 to 0.5b for common sense reasoning, Qwen 2.5 to 1.5b for math and coding, and Qwen 2.5-VL3b for multimodal tasks. Our results show that D&D consistently outperforms foundational LLMs across all tasks. Its drag-and-drop capability allows it to create task-specific parameters that perform better than those of foundational LLMs, despite their extensive pre-training. Next, we visualize the original and generated parameters. We observe that the original parameters display diverse patterns in the weight space, forming distinct clusters. Notably, even parameters that are close to those tuned on the target dataset, ARC-C, can show a significant performance gap, with scores of 19.1% compared to 40.7%. After training on models with unique features, D&D can generate parameters for the target dataset in a zero-shot manner. These generated parameters are not only close to the originals in the weight space but also outperform full-shot tuning, achieving 51.6% compared to 40.7%. This illustrates the effectiveness of the drag-and-drop effect. Regarding parameter generation, we focus on training model checkpoints to create high-performing parameters, both seen and unseen during training. Previous research has aimed to learn distributions over parameters but often struggles to replicate the original model's performance. With advancements in diffusion models, we utilize the latent diffusion architecture to generate high-performing parameters. Using Mamba and an effective tokenization strategy, we can generate 200 million parameters in just minutes. In terms of conditional generation, methods like cond-pdiff, TINA, and ORAL explore text-controlled parameter generation. Our approach, however, uses prompts from novel datasets as conditions, allowing us to better capture the relationship between parameters and datasets, enabling us to generate effective parameters for new datasets.